Good day, everyone. So, this time we are going to discuss the 19th century of mathematics. So, let me start with our learning objectives. So, the first is what were the nature of mathematics during 19th century? So, we'll know about it later on, as well as we will know what were the contributions on this period and who were the prominent persons during this time. And of course, lastly, we have what were the contributions to math development. To start with, let me start with the time frame and nature of mathematics. So the era in which engineering applied mathematics arose, and they often call the 19th century mathematics as the age of revolution, which began on late 18th century to 19th century all throughout Europe, which primarily contributed by the two countries, which are Germany and France. So which means that on 19th century, often called as the age of revolution in mathematics, was a transformative period for engineering and applied mathematics. This is the beginning or in the beginning of 18th century and continuing throughout the 19th century, Germany and France were the key contributors. And mathematicians, like Gauss, Raymond Fourier, and Laplace made groundbreaking advancement in areas like calculus, differential equations, and mathematical analysis. Also, mathematical or these developments help applied mathematics to real-world problems in physics, engineering, and shaping technology and industrial process. So those were the time frame and nature of mathematics during 19th century. So let's proceed with the materials that were used during that time. So of course, they have used papers, as well as plasters. Plasters are the pasty composition of lime or gypsum, water, and sand. This hardens on drying and is used for coating walls, ceiling, and partitions. So they also use plasters during that time as the material used in order for them to contribute to mathematics. And the next one is strings. These are thin ropes made of twisted threads. So they also use strings during this time or that time. And the materials and the tools that was used on 19th century, these are the research journals. So research journals were established to disseminate mathematical knowledge. Also, we have printing press. The printing press allowed people to publish books and pamphlets, as well as we have here the universities. So universities became centers for learning. And furthermore, algebra as well began to use variables to represent things other than numbers, such as matrices, modular integers, geometric transformations. And we also have the complex numbers. The French writers such as John Argand discussed complex numbers from a quasi-philosophical standpoint. And so much more about that one. We will proceed with the contribution to people's life and to the development of mathematics. So during 19th century, most of the powerful abstract mathematical theories in the use of today originated in the 19th century. So combinations of binary digits are used in various ways to build up higher level building blocks like gates, registers, arithmetic processors, and etc. Which, because of Boolean algebra, atmosphere's impact on retaining heat, now known as the greenhouse effect, which was discovered through a Fourier series and led to thermodynamics. So, which means that in 19th century, mathematical advancement have had profound implications across multiple domains. Boolean algebra as well underpins modern computing, enabling everything from basic circuits to complex algorithms. And also, for years, analysis continues to be vital in fields like signal processing, weather forecasting, and climate sciences. The application of these mathematical principles not only advanced theoretical knowledge but also paved the way for technological innovations, particularly in computing energy systems and environmental studies, which shapes the world as we know it today. So right now there are actually a lot of people who contribute to the 19th century. So let me start with the first prominent people that we're going to discuss, which is Joseph Fourier, which was born in 1768 to 1830. So Fourier showed how conduction of heat in solid bodies may be analyzed in terms of infinite mathematical series, now called by his name, the Fourier series. And he was also a French mathematician known as the Egyptologist and administrator, which exerted strong influence on mathematical physics through his theory analytique de la Chaleur. So that is the analytical theory of heart on 1822. Also, with regards to Fourier's series, this is a periodic function that can be expressed as the sum of the infinite series and sines as well as the cosines. So they are still powerful tools, pure and applied mathematics as of this time. And with this, Fourier series is a way to represent periodic function as the sum of sines and cosines. This approach, as well by John, allows complex periodic function to be broken down into simpler trigonometric components. And Fourier series remain powerful tool in both pure and applied mathematics. In pure mathematics, they help in study of functions, convergence, and analysis. And in applied mathematics, they are used in fields such as signal processing, heat conduction, and communication systems, where complex waveforms and signals can be analyzed as well and processed more easily using their trigonometric component. Okay, and let's proceed with the second prominent person, which is John Robert Argand. So John Robert Argand is an accountant and bookkeeper in Paris who was only an amateur mathematician. So he also published his paper on how complex numbers of the form a plus bi, which is I as the imaginary, and could be represented as geometric diagrams and be manipulated using trigonometry and vectors. And we also have his contribution, which is the Argand diagram, which is complex numbers are represented geometrically using Cartesian axis and horizontal coordinates representing real part of numbers and vertical coordinate the complex part. So the Argand diagram is a way to represent complex numbers as what I have stated a while ago. And on this diagram, a complex number which is like z is equals to a plus bi and is represented point or a vector in complex plane. So with this, the horizontal axis or the x-axis represents the real part of the complex. And y-axis is the vertical axis represented by b. So with this, we can state that this graphical representation makes it easier to visualize operations which complex numbers such as addition, multiplication, and finding magnitudes and arguments as well, which are angles. And right now, let's proceed with Évariste Galois. He was born on the year 1811 and died on the year 1832. And he was a radical Republican and something of a romantic figure in French mathematical history. Also, At the tender age of 17, he began making fundamental discoveries in the theory of polynomial equations. He was also and effectively proved that there can be no general formula for solving quintic equation, which is the polynomials including a term of x to the power of 5. He was the first to use the term group in the modern mathematical sense of permutation group, or the foreshadowing the modern field of group theory, and this fertile approach, now known as the Galois theory. Okay, so with regards to Galois, he was made groundbreaking contribution to mathematics as well, particularly on the study of polynomial equations and group theory. He proved that there is no general formula for solving quintic equations. And this equation terms as x to the power of 5, which built on the work of earlier mathematicians. Galois used group theory as well to show that solution to such equation cannot be expressed in terms of radicals, marking the end of the search for general solutions. And additionally, Galois introduced the concept of groups in its modern sense, particularly through permutation groups. This approach laid as well the foundation for Galois theory, a key area in abstract algebra that links field theory and group theory, and has profound implication in solving equations and understanding symmetries. Galois theory today is also central topic in mathematics, particularly in algebra and number theory. And those are all for Galois. Let's proceed with the next prominent person, which is Carl Friedrich Gauss. At the age of 15, he noticed that a rough pattern or trend as the numbers increased by 10, the probability of prime numbers occurring reduced by a factor about 2. And he is also considered as the prince of mathematicians and the greatest mathematician since antiquity. He is a German mathematician, ranked as one of the history's most influential mathematicians. So, Carl Friedrich Gauss, or Gauss, was entitled to be the prince of mathematicians, and he was also a German mathematician widely regarded as one of the most influential figures in the history of mathematics, often called as greatest mathematician since antiquity. Also, Gauss made groundbreaking contributions as well across many fields, and that includes number theory, algebra, statistics, astronomy, as well as geometry. His works in number theory, particularly in Disquisitiones Arithmeticae, laid to the foundation for modern mathematics, as well as he also made significant advances in Gaussian elimination, a method for solving system of linear equation, and Gaussian curvative in geometry, and Gaussian distribution in statistics as well. His discoveries continue to influence mathematics, physics, and engineering as of today. In addition to that, at the age of 19, he constructed the hitherto unknown regular 17-sided figure using only a ruler and compass. So, which means that Carl Gauss was the one who was able to construct the heptadecagon, or the seven-sided polygon. And also, with regards to this, he was also what I mean is he was able to construct the seven-sided polygon just using the ruler and a compass. And in addition to Gauss' description, similar to Organ's diagram, but Gauss was certainly responsible for popularizing it and also formally introduced the standard notation, which is A plus BI for complex numbers. Gauss made a prediction on planetoid Sarasan, its position which varied greatly from the prediction of the most other astronomers of the time, while he is the director of astronomical observatory in Göttingen. He conceptualizes well through logarithmic calculations in his head. So there are a lot of contributions that Gauss gave to mathematics as of this moment. And it is also at the time a prediction from other astronomers were inaccurate, but Gauss' innovative use of logarithmic calculations helped him refine the orbit with only a few observations. With this, his success in predicting Ceres' position demonstrated the power of mathematical methods in astronomy and solidified his reputation as a leading scientist. But wait, there's more. There's still some of additional information regarding Gauss. So did you know that Gauss also introduced known as the Gaussian distribution, the Gaussian function, and the Gaussian error curve? He showed how probability could be represented by a bell shape or a normal curve. Moreover, a contribution in differential geometry, Gaussian curvative, an intrinsic measure of curvative dependent on how distances are measured on the surface. Not only the way it is embedded in space, as what Gauss have discovered, and Gaussian curvative is a concept in differential geometry introduced by which is introduced by him. It measured the intrinsic curvative of a surface, which means it depends on the surface itself and not on how it's embedded on space. Specifically, Gaussian curvative is the product of principal curvatures at the given point on the surface. In both principal curvatures are positive, the surface is bent in the same direction like a sphere, resulting in positive curvature. If the curvatures have opposite signs like a saddle, the curvature is negative. If the curvatures are zero, like a flat plane, the curvature is also zero. This measure is intrinsic because it can be determined solely by distances and angles measured on the surface. Without reference to surrounding space, Gauss' famous theorem egregium states that Gaussian curvature is preserved, meaning that preserved under local isometries, meaning that curvature remains unchanged if the surface is deformed without stretching. So those are all for Carl Friedrich Gauss. Let's proceed with another prominent person which will be discussed by Mr. John Michael. Thank you so much.
So thank you for that wonderful introduction and explanation until the prominent person of Miss Juraza Tuting. So continuing where she left off, the next prominent person is Janos Bolyai or Johann Bolyai, born in 1802 and died in 1860. Johann Bolyai was a Hungarian mathematician. His father, which is his own teacher, Farkas Bolyai, was himself a student of the great German mathematician Gauss. He became interested to Euclid's fifth postulate and concluded that it is possible to have consistent geometries that were independent of the parallel postulate. So ang kaning Euclid's fifth postulate is mo ni ang parallel postulate, no, nga katong parallel lines o naay line nga na-fall down sa iyaha. Bolyai explored what he called imaginary geometry. So ang iyang giingon sa first slide is It is possible to have consistent geometries that were independent of the parallel postulate, so it is expected nga ang iyang na-create nga geometry or concept of geometry is wala nag-based sa parallel postulate. It's actually the contradiction of it. So it is called imaginary geometry, now known as hyperbolic geometry. The geometry of curved spaces on a saddle-shaped plane. Ang kaning curved spaces on a saddle-shaped plane, if dili na ninyo ma-picture out, to help you is, kuan lang, hunahunaon ninyo nga, ang kaning nga plane is, or kaning nga space is mura siya og kanang isa ka piece sa Pringle, where the angles of a triangle did not add up to 180 degrees and apparently parallel lines were not actually parallel. In curved space, the shortest distance between 2 points A and B is actually a curve, or also called geodesic, and not a straight line. So the sum of angles is less than 180 degrees. So sa iyahang hyperbolic geometry is wala ang sense nga na ay straight line. Ang iyaha is curve kay tungod sa iyang gamit nga space or plane or I mean mura og na, structure nga dili siya plane unlike sa kang Euclid. So isa ni si Bolyai sa mga naka-create independently sa hyperbolic geometry. Kaya napa may isa pod ka mathematician nga naka-think or naka-create pod ani nga concept though wala sila'y collaboration, which is our next prominent person. Nikolai Lobachevsky, born in 1792 and died in 1856. Nikolai Ivanovich Lobachevsky is a Russian mathematician. So kung si Bolyai is from Hungary, si Nikolai Lobachevsky is from Russia. Also been working very similar lines as Bolyai to develop a geometry, but Euclid's fifth postulate did not apply. His work on hyperbolic geometry was first reported in 1826 and published in 1830, although it did not have general circulation until some time later. This early non-Euclidean geometry is now often referred to as Lobachevskian geometry or Bolyai-Lobachevskian geometry. This geometry satisfies all of Euclid's postulates except the parallel postulate. There are no similar triangles in hyperbolic geometry, which the sum of angles of a triangle is less than 180 degrees, and triangles with the same angles have the same areas. So wala niya na-satisfy ang fifth postulate ni Euclid tungod kay ang kang Euclid is parallel postulate. So two straight lines. Ya, dili man mahimo nga naay straight line sa isa ka curve nga space, which is mao ang gihimo nga medium or like mao ang gihimo nga sakto lagi medium sa hyperbolic nga geometry, which is curve or saddle shape nga um, space. And there are no similar triangles in hyperbolic geometry. Gitangtang pod niya ang concept nga every angle of a triangle is equal to 180 degrees. Kay wala may straight nga line, so most likely ang lines nga makita sa isa ka triangle is geodesic or slightly curved. Maong walay 180 degrees nga total sa angles. Instead, napulihan ang kanang concept into triangles with the same angles have the same areas. So our next prominent person is Bernhard Riemann, born in 1826 and died in 1866. Bernhard Riemann was another mathematical giant hailing from northern Germany. Indeed, he was one of the very few who benefited from the support and patronage of Gauss. So, karon murag ma-feel na nato or makasabot na tanong anong ang title nga nadawat ni Gauss is Prince of Mathematics na very influential gid siya nga person or figure in the mathematical field. So, Riemann developed a type of non-Euclidean geometry different to the hyperbolic geometry of Bolyai and Lobachevsky, which has come to be known as elliptic geometry. So ang elliptic geometry is a type of non-Euclidean geometry that happens on a curved spherical surface instead of a flat plane. Um, naa siya three ka-characteristics. So first is the same sa hyperbolic na walay parallel lines. In elliptic geometry, walay parallel lines kay any two lines will eventually meet like how our longitude lines on the globe works. The second is triangles are different. So same gyapon siya sa hyperbolic geometry. The angles in a triangle always add up to more than 180 degrees, unlike Euclidean's geometry, where they add up exactly 180 degrees. And the last characteristics is the curved space. Imagine the surface of a sphere. Shapes and distances work differently on this curved surface than they do on a flat surface. So mo na ang characteristic sa yang elliptic geometry. Correction day, sayop day ko. So sa elliptic geometry is walay parallel lines kay magmeet ang duha ka line. Sa hyperbolic geometry is naay parallel lines, it's just that dili siya totally straight line. Pero same siya sa kuan. Concept gihapon ni Euclid nga naay parallel lines. Dili lang siya straight line. Sorry. And unlike sa hyperbolic geometry, ang kaning elliptic geometry is positive, positive curvature kay sphere man. Ang katong hyperbolic geometry is negative curvature tungod kay saddle-like shape man siya. With his Riemann metric, he believed that each top of the fingers or the highest point in 3D models are the zeros. So unsa man ni ang Riemann metric? So ang kaning Riemann metric is a mathematical tool used to measure distance and angles on curved surfaces or spaces. So ang Riemann metric is gikuha ra pud sa apelyido ni Bernard Riemann. Siya man pud ang nag-develop, no? So unsa may gamit ani or unsa may like gigamitan ani. So ang Riemann metric defines how to calculate the length of curves, angles between vectors, and areas or volumes on a curved surface or space. It generalizes the idea of distance from flat or Euclidean geometry to curved spaces. So murag iyang gitransfer ang anang idea ni Euclid on how to measure distance on a flat plane surface into a curved spaces or spherical spaces. Ang kaning sa example niya nga fingers or highest point in 3D models kay mura ni siya og kuan. Mura ni siya og example nga iyahang gi-think. Like example nga mura og ni stand out sa lain. So fingers or the highest point in 3D models as zeros. So an example of this is think of a mountain range with several peaks. The peaks or highest points are special because they stand out. In Riemann's framework, these peaks might serve as key reference points or zeros for understanding the overall shape and curvature of the mountain range. So ang highest point sa mountain range or finger is mo yung gihimo as zero sa iyahang kanang pag-solve sa total curvature or distance nga mura siya og like point isa ka point nga diha siya mag-start in computing the overall curvature or like anchor gani sa distance nga diha siya magsugod and measure to where distance ang iyang ganahan i-measure. So our next prominent person is George Boole, born in 1815 and died in 1864. A British mathematician and philosopher. Came to see logic as principally a discipline of mathematics, rather than of philosophy. He came up with a type of linguistic algebra now known as Boolean algebra. The three most basic operations of this algebra were and, or, and not. He made algebraic identities as x or y equals y or x, not x equals x, not x and y equals not x or not y, and etc. He also developed a novel approach based on a binary system, processing only two objects represented by 1 and 0. That could be meant yes or no, or on and off, and many more. So, to elaborate the operations on Boolean algebra, the and, or, and not, here are the examples. For and, both inputs must be true or 1 for the result to be true. Example of this is 1 times 1 equals 1 or true. But 1 times 0 is 0 or false. Kaya ingon man siya nga rin, no, nga only two objects or kaning binary system niya processing only two objects represented by 1 and 0 or yes or no or true or false. So kung mogamit ka og true or 1 times a true, it will become true. But if you use 1 or true and a false, then mahimo siya og false. So that's it. Very basic or simple sa yang and. The next is for the or operation. At least one input must be true or 1 for the result to be true. An example of this is an example sa or is at least one input must be true matano. So the first example is 1 plus 0 equals 1, which is true. Pero nasa exception. Though ang iyang gingon is at least one input must be true for the result to be true, na exception for the false. True ang mogamit ka og false pero true kung duha ka false imong gigamit. So an example of that is 0 plus 0 equals 0, which is true, di ba? And for not operation, it reverses the values. True becomes false and false becomes true. So 1 is true man and 0 is false. So an example for this is a not 1 equals 0. So ang imong input is true, ang imong output is false. So an example na as I have said is not 1, not 1 is 1 is true equals 0. 0 is false. And kung ang imong input is false, ang imong output is true. So if not 0 equals 1 or true. If not false, then true. So that's it for Boolean algebra. Very simple and easy. So our next prominent person is George Cantor, born 1845 and died in 1918. German George Cantor was an outstanding violinist, but an even more outstanding mathematician. After which he turned his attention to calculus, solving a difficult open problem on the uniqueness of the representation of a function by trigonometric series. He realized that even though the multiples of 10 were clearly a subset of the natural numbers, the two series could be paired up on a one-to-one basis. The process called bijection. So, unsa man ni ang bijection? Ang bijection is kuan. So, ang example yang gihatag nga rin is natural numbers o multiples of 10. So, ang natural numbers is the counting numbers. 1, 2, 3, 4, 5, and so on and so forth. And the multiples of 10 is 10, 20, 30, 40, and to infinity. So, it may seem nga ang multiples of 10 is fewer than the natural numbers, but the bijection or the process called bijection is giprove niya nga same or show that they were the same sizes of infinite sets in that they had the same number of elements. So para mas dali masabtan atong ikuan like even though fewer ang or mahuna-hunaan na to nga fewer ang multiples of 10 nga set or fewer ang elements sa multiple of tens nga set is same ra gyud siya og number of elements sa natural numbers. So para mas masabtan na to is ato siyang i-pair like sa babaw is the natural numbers 1, 2, 3, 4, 5 then sa ubos is ang multiples of 10 or 10, 20, 30, 40. So atong i-pair ang 1 ug 10. Ang 2 ug 20, 3 and 30, 4 and 40, 5 and 50, and so on and so forth. Layon, diha na to makuan nga. This is that process is called bijection. And by that, atong ma-prove nga all the natural numbers or all the elements of the natural number set is the same number of elements pod sa multiples of 10 nga set. So na-prove niya no or gi-paired awayang gistoryari. Series can be paired up on a one-to-one basis. So same sa atong gibuhat, 1 is to 10, 2 is to 20, 3 is to 30, and so on and so forth. So that process is called bijection. He said that there are infinite sets which cannot be put into one-to-one correspondence. So kani is contradictory sa iyang unang istorya. With the infinite set of natural numbers, such sets are now known as uncountable sets. The size of infinite sets is now treated by the theory of cardinal numbers, which focuses on the size of the set of the natural numbers. From this, he coined the word transfinite, which means numbers that are infinite in the sense that they are larger than all finite numbers, yet not necessarily absolutely infinite. So kung ang countable numbers or ang counting numbers is infinite sets or countable sets or countable infinity, ang kaning sets nga dili mo one-to-one correspondence sa infinite set is called uncountable sets or uncountable infinity. The size of infinite sets is now treated with the theory of cardinal. So ari mo sud ang iyang transfinite. So ang ako ang mahatag nga example ani is ako ang na-search is kung ang countable numbers is magsugod og 0 and 1, atong hunahunahon nga unsa man ang naa tunga sa 0 and 1, which is 0.1, 0.2. So mao na siya ang uncountable infinity or uncountable set. Kay daghan di man na siya maihap og pila na siya ang naa diha tunga sa 0, usa siya nahimo og 1. So mao na ang iyang concept of transfinite. So hunahunahon nimo unsa 0.1 or 0.00000001, 0.0002 ana hangtod mahimo siya og 1. So mao na ang uncountable sets or uncountable infinity or infinite. He used the Hebrew letter Aleph. He defined Aleph null or Aleph naught as the cardinality of the countably infinite set of natural numbers. Aleph 1 as the next larger cardinality. So ang Aleph naught or Aleph null is mao ang counting numbers. Ang Aleph 1 is mao to ang kato akong gi-example nga 0.000 or 0.0001 or 0.1 nga kana in between sa duha ka counting numbers. The real origin of set theory, which has since become a fundamental part of modern mathematics, and its basic concepts are used throughout all various branches of mathematics. So ang iyang foundings day ang mao ang origin or fundamentals or like adto gyud nagsugod ang set theory, which has since become a fundamental part of modern mathematics. So gigamit gyapon day iyang mga anang foundings or discoveries hangtod karon, and its basic concepts are used throughout all the various branches of mathematics. So even though complicated ang ihang napangita is gigamit gyapon siya throughout the various branches of mathematics theory. Our last but not the least prominent person for the 19th century is Henri Poincaré, born 1854 and died 1912. Paris was a great center for world mathematics towards the end of 19th century, and Henri Poincaré was one of its leading lights in almost all fields. He is sometimes called the last universalist. He realized that even a very small change in his initial conditions would lead to vastly different orbits, led indirectly to what we know as chaos theory, a burgeoning field of mathematics. Common example is the flap of a butterfly's wings leading to a motion like a tornado on the other side of the world. So though murag complicated ang yang gihatag nga example, so to make it simpler no, and relate it to a certain scenario or situation is maghatag og another example as a context ani butterfly wings, flapping of the butterfly wings. So assume nga atong i-try og predict ang weather using sa dagan sa air. So kay bawo na ta og unsa ang dagan sa air karon. Atong nasukod ang dagan sa air for that specific day. Then we try to predict unsa ang weather for the following day or the following month. Ana. So atong na predict is sunny baron or muuwan, pero ang kaning flap of the butterfly wings is though gamay kaayo siya nga like kanang unsa man, gamay kaayo siya nga commotion or happenings sa air nga ato ang gi-studyhan to predict mo cause siya og dako nga effects on the long run, which is referred to or called chaos theory. A very simple example of chaos theory, no? So ang chaos theory ay is nag-prove or ni-prove na a long-term prediction is practically impossible. So as tiny as a flap of a butterfly's wings can lead to a chaos to our initial conditions nga ato ang nakuha as in pursuing nga ato i-predict ang weather on the long run. So that's it for his chaos theory. Poincare also developed the science of topology, which Leonhard Euler had heralded with his solution to the famous seven bridges of Königsberg problem. In theoretical physics, he made a symmetrical presentations of Lorentz transformation in 1905, which helped Einstein for theory of relativity. So, ang kaniyang topology is a branch of mathematics that deals with the properties of space that remain unchanged under continuous transformations. This includes stretching or bending but not tearing or cutting. Think of it as studying the stretchiness or flexibilities of shapes. So kaniyang concept nga kani is mao ang kuan like nitabang mostly sa katong mathematicians nga nag-study pod sa kanang concept sa shapes or like Einstein sa yang relativity, theory of relativity nga katong mag-bend no. So isa po day ni ka groundbreaking discovery ang iyahang kuan mathematics nga na discover. So moving on, contributions to the development of mathematics. Unsa may na-contribute sa 19th century sa development sa mathematics. So the first one is imaginary numbers became widely accepted in the mathematical community. Imaginary numbers such like katong sa uncountable infinity katong na discuss nato baguhay lang katong 0.001, 0.1 kato na-accept na siya sa mathematical community. The second one is complex number were thought of as pairs of real numbers with rules for addition and multiplication. So same gihapon sa katong kuan, same gihapon sa akong example nga una katong 0.1 daw mao akong gihatag sa imaginary numbers. Ang simple example for imaginary numbers are the negatives, or the negative 1, negative 2, and so on and so forth. So complex numbers were thought of as pairs of real numbers. So pares na siya sa real numbers, katong 0, 1, 2, 3, with rules for addition and multiplication. So gi-apply na pod nila ang basic operations of mathematics sa um, complex or imaginary numbers. The third is mathematicians began to use variables to represent things other than numbers, such as matrices, modular integers, and geometric transformations. This led to the study of algebraic structures, which include group theory, field theory, and vector spaces. The fourth is mathematicians clarified different types of numbers, including integers, rational numbers and irrational numbers. So na-clarify na day nga rin no, ang different types of numbers. Nga dili lang day isa ra ka type of number which is the counting numbers. Napo day lain like integers, rational and irrational. The last is projective geometry emerged in post. revolutionary friends. So, ang projective geometry is katuning murag imaginary geometry, katong hyperbolic geometry. So, and that's all for 19th century mathematics. Thank you guys for listening. I hope you learned something through our discussions. Thank you.